So this part's going to deal with pressure. When equilibrium involves pressure, we're going to use Kp, which is the equilibrium constant involving pressure. It's solved the exact same way as K, but you're going to use pressures at equilibrium instead of concentrations. So here we have a problem where we want to calculate Kp. First thing we need to do is write the Kp expression. And so there's a little bit different than Kc or just regular K. We're going to have the pressure of our product, which is NaOCl. You need to specify what that pressure is. And those are parentheses, not brackets. Brackets indicate concentration. And then we have our reactants on bottom. So if you notice, it looks very similar, except now we have to put P and we don't have brackets. Very important that you have those two things. Now we just plug in everything from our data. These again were pressures at equilibrium. They do all have to be in the same pressure. And so we determine our Kp to be 1920. We can relate K to Kp by using the equation Kp equals K times RT to the power of delta N. In this equation, Kp is our gas equilibrium constant. K or Kc is the regular equilibrium constant. R is the gas law constant since we're dealing with gases, and that's 0.0821 liters times atmospheres over moles times Kelvin. Temperature is T, and that needs to be in kelvins. And delta N is the sum of the coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. So it's gas products minus gas reactants. If delta N is equal to 0, then K equals Kp, because the RT delta N would cancel itself out. So in the previous problem, we calculated Kp for this reaction. Now, using that Kp value, we're going to find K for the same equation. So we're going to use the equation that we just talked about, Kp equals K RT delta N. We know the Kp, so ignore that work. It should be 1920 for Kp. We do not know K, so those two should be reversed. We know R, because it's 0.0821, it's the gas law constant. For temperature, remember we add 273, so that's 298. And to find my delta N, I have all gases, so that product is a gas. And so delta N is, I have 2 products of gas minus 3 reactants of gas, giving me a -1. And again, I have 1920 on the other side, so it's 1920 over the rest of that, and it gives us 4.7 times 10 to the 4th. Go ahead and calculate your Kp for this reaction given your K. Restart when you think you have it. So in this problem they gave you Kp and we're looking for K. So we need to plug it into our Kp equals K expression. We know our K, we know R. We need to convert that temperature to Kelvin, which is 433. And then to find our delta N, remember it's products minus reactants. I have 9 gas products minus 10 gaseous reactants, which also gives me a -1. Plugging that in, I get a 0.0128. if I have different phases in my equation, then that's what we call heterogeneous equilibrium. You must omit all pure solids and liquids from the equilibrium expression. That's very important and causes people to miss problems every year on the test. The reason is because you can't change the concentration of pure solids and liquids. They're always 100%. So if I was to write the K expression for these reactions, the first thing I would need to do is actually write the reaction from the words, including state symbols. So solid phosphorus pentachloride decomposes into phosphorus trichloride liquid and chlorine gas. So again, I'm going to have to omit all pure solids and liquids. So that's a solid, so I omit it. Liquid, omit it, and gas stays in there. Gas is an aqueous stay. So my K expression, I have products over reactants. I don't have any reactants, so I just leave it, or I could put over 1. And again, make sure that it's balanced. For my Kp, it's the exact same thing, except I'm going to have pressure of chlorine. And I can put the parentheses. I don't really need the parentheses since I only have one thing though. And it's not raised to a power. Down at the bottom we have copper 2 sulfate, pentahydrate. Remember that means we have 5 waters attached and it's solid. And when that decomposes, we're going to have water and copper 2 sulfate. Water a gas and copper 2 sulfate a solid. We do have to balance. We have a solid, so we eliminate. A solid, so we eliminate. And again, we have just a product. So our K is equal to the concentration of water. And we have a coefficient this time, so it's raised to the power of 5. My Kp, again, would just be pressure of water. This time I do need the parentheses because I'm raising it to the power of 5. On that first reaction, had the reaction been switched and my chlorine been on the reactant side and that's all I was left with, my K would have been 1 over chlorine because I didn't have any products if that was the case.